Let's talk about displacement versus total distance. So at the top of the page here, you can see sort of a at least theoretical summary of the difference between these two things. So we're assuming we have an application problem where we're given a formula for the velocity of a moving object. Typically, it's a particle moving along a line. So if you have v of t, the velocity function, the displacement of the particle between time A and time B is just the definite integral of the velocity function on that time interval. So what we mean by displacement is just the difference between where you ended and where you started. So for example, if the particle was moving all around during the time interval and then landed back where it started, its displacement would be 0, even though it traveled around a bunch. Total distance doesn't have that same issue, right? So we're still integrating the velocity function, but these absolute values are implying like we need every single inch or mile or meter or whatever we're measuring it in to count as positive velocity so that it all adds up and none of it cancels out. All right, so let's see this in a couple of examples. Our first example has a particle moving with velocity 2t minus 4. I suppose I didn't put units in this. I probably should. Why don't we say meters per second? And then we'll go from t equals 1 second to t equals 4 seconds. Okay, so displacement is the straightforward one. So this one, it's going to be like the net change between your ending and beginning values. So this will just be straight up the integral from 1 to 4 of this velocity function 2t minus 4. I'll compute my antiderivative, plug, subtract, and we'll get the net change between the two. So 2t's antiderivative is t squared, 4 is 4t, and we'll evaluate from 1 to 4. With a 4 in it, we have 4 squared minus 4 times 4. And then with a 1 in it, 1 squared minus 4 times 1. 4 squared minus 4 squared, this whole thing actually comes out to 0. And then this one here, we have 1 minus 4 is negative 3. So 0 minus negative 3 gives me positive 3 meters. All right, so overall, between the first and fourth second, this particle went forward 3 meters, but it might have gone back and forward a bunch and then stopped 3 meters forward. Okay, so now let's compute the total distance traveled over the same time interval, and we'll compare it with that 3. So theoretically, what we're doing is integrating the absolute value of 2t minus 4, but in a practical sense, that doesn't actually help us compute. What we need to do is figure out where this function 2t minus 4 was negative, having like negative output values, so that we can kind of forcibly make that net area count positive instead. So I want to sketch a graph of 2t minus 4 to kind of take a peek at that. This is a straight line. So all I would need is 2 different t comma v points instead of x, y. So I just need to connect 2 points here. One thing, like a feature that's going to be really important in this graph sketch is where we're crossing the x-axis. So where this thing actually equals 0. So I'm actually going to compute that exactly, set it equal to 0 and solve. It's going to cross the x-axis at 2. That's right here. And then why don't I also plug in 0? So 2 times 0 minus 4 is negative 4. So 0, negative 4 is another point, and it's a straight line, so we'll just kind of roughly connect these. All right, so the reason I needed this sketch, we'll come back to the original task here. We want to know total distance from 1 to 4. So I'm going to mark those t values in this image, 1 to 4. So we can see the little chunk between 1 and 2. When we integrated in the first part of this problem, this counted as negative area, and it canceled out some of this positive area here. So what we want to do is add up the area of the red as positive plus the area of the blue also positive. So this tells me I need to split the integral from 1 to 2 and then 2 to 4. So I'll say TD for total distance. We'll have the integral 1 to 2 of my velocity function. So this is the part that was going to come out negative. So I essentially want to compute this number and just take the positive version of it. So I'll just put a times -1 on the integral, which will essentially just take away the negative part. And then the rest of it from 2 to 4 is going to come out positive because it's this blue area right here. So this one gets to stay normal because it was already counting positively. All right, and now we compute. Very similar as the above work here. We'll have the same antiderivative. T squared minus 4t. T squared minus 4t. And keeping that minus sign. So I'm writing this minus sign as a really dramatic -1 out front, mostly just so that my eyes don't forget that it's there. At some point, I'm going to have to multiply that in. Okay, so if I plug in 2 to this formula, I have 4 minus 8. If I plug in 1 to this formula, I have 1 minus 4. The 4, I get a 0 again, just like above. And then with a 2 in it, I have 2 squared is 4 minus 8. A lot of similar things here, but they're not totally canceling each other. 4 minus 8 is -4. 1 minus 4 is -3. So here I have -4 minus -3. So it's -4 plus 3 is -1. So this -1 right here, that was the negative area that was counting from this red triangle here. So now we're doing, okay, -1 times that, which is going to make it count as a +1 area instead. Over here in the second bracket, I'm expecting this area to come out, or this integral to come out positive, because it should just be all this area above the x-axis. 16 minus 16 is 0. 4 minus 8 is -4. 0 minus -4 is 4. All right, so I have 1 plus 4 is 5. So even though the net change or displacement was 3 meters, the particle actually traveled 5 meters during the trip. Okay, let's talk about at least the beginning of another one that has a more complicated velocity function. So let's say same setup, but the velocity function is t squared minus 5t. We're just going to talk about the setup here, and we'll skip the number crunching in the video. All right, so if we want the displacement of the particle from 0 to 7, we would just do the definite integral from 0 to 7 of this function, antiderivative, plug, subtract. The total distance traveled is a more complicated thing, right? That's what we were doing here. So I need to figure out on the interval 0 to 7, where is this function positive and where is it negative? Because that's going to give me positive area, negative area in the total. All right, so I need to investigate v of t equals t squared minus 5t. I don't need a perfect, beautiful graph. What I really am interested in here is where it crosses the x-axis, where it's positive, where it's negative. So again, I'm going to start by setting it equal to 0 and solving so I can get those x-intercepts perfect. So I have t equals 0, t equals 5. Having 2 solutions here versus 1 here makes sense because that was a line. This is a quadratic. Okay, so I have x-intercepts at 0 and 5, and I have options for how to fill in the rest of this information. One thing I could do is look back at this original formula and see that t squared, and I say, oh, well, this is a quadratic. It has, so it's a parabola shape, and it has a positive leading coefficient of 1, so I know it opens upwards like that. If you get a formula, either this one or a different one, that you don't feel comfortable making that judgment call, what you could do instead is test points, almost like it's a first derivative test, right? So plug into this velocity function a negative number, let's say -2, and you'll get a positive output. So you're like, okay, I'm above the axis. And then if you test a number between 0 and 5, you'll get negative, so you're below, and then finally above. So even if the shape of the graph isn't right, you at least have the information you need. Okay, so once we get this rough picture, we want to remember what the interval of concern was here at 0 to 7. So within 0 to 7, 0 to 5 was contributing negative area to the problem. So I'm going to break off the integral 0 to 5 and just put a times minus 1 in front of it like we did here, so that all this area where it comes out negative, we're going to make it positive. So our total distance would be negative integral 0 to 5, and then plus regular integral 5 to 7 of the velocity function, because 5 to 7, it was contributing positively anyways.